clear as I can about for both the electric and H field and then for the power, all right? So if you looked at some of that stuff and you were confused, it's understandable. I'm just going to try, I'm going to note set out, to really put this all in perspective and show you what you need to know about arrays from a perspective of this is that if you're an electrical engineer, electrical and computer engineer, you're out in the real world, and you're asked to design an array to do something, this is the thing I would want you to know. Now I want to say one other thing. The real benefit of arrays is this. It tremendously increases the directivity / gain of an antenna, and it enhances the amount of power you can put at a given point. Right? That's the real benefit. And there are many types of arrays. We're just looking at a linear array, constant current with a constant phase shift. There are two-dimensional arrays. There's probably even three-dimensional now arrays, where you just have elements that repeat themselves, step and repeat the exact same element, all through an array. And it's designed to do one and only one. Well, primary thing it's designed to do is to focus the power at different points. Right? That's what an array does. So let's start by saying if we have the isotropic array, what I want to do here is talk about the fields first, and then talk about the power, which is disproportional to E squared. So you'll understand that this is not that big of a jump. So for isotropic arrays, you all have a test there or something? We're missing a bunch of people and they're really quiet.
Maybe because of the rain.
Is that what it is? Just the weather? All right, well, I mean, it's okay. I understand. For isotropic arrays, by that I mean, I should say, the sources are isotropic. I'm going to say the actual electric field from the individual elements, because it's isotropic, is just K times some I naught over 4 pi r e to the minus j beta r. So, and you can put the vector direction here, but you don't have to. That's the element pattern. You with me? So if we have a bunch of these elements in an array, this is where I was last time. And we have 1, 2, 3, n minus, or n arrays, n points, all right, n elements. These elements all have the same magnitude of current, but there's going to be a progressive phase. Now, if you look at Dr. Wentworth's book in the section on arrays, on page, I gotta find it. This shows us really on bottom page 273. He's not doing it quite the way I'm doing it. I prefer to do it this way. I'm showing you the actual current values and the progressive phase changes. The magnitude is the same. There's a progressive phase change. Here, the angle would be phi. Now, what we did last time is we adapted something to make the shorthand notation look better. So we said we're going to define something that I called psi, or pitchfork, as beta d cosine of phi plus alpha. Do you all remember that? That was a shorthand way of compacting both beta d and phi and alpha all into one term, because it's going to repeat all the time, okay? That's the reason I'm doing it. Now, if we have this, we found out that the total electric field from that was equal to the element pattern K times I naught over 4 pi R. And R I didn't show you this, but R is a vector distance out to a very distant point, some point where you want the electric field. And here we're assuming R is much, much greater than the number of elements times the spacing between the elements. So we're in the far field. This is the real thing I'm driving. We can neglect all the near field stuff. We're a long ways away. This is the E field from an individual element. It's the individual element right there. And it's multiplied by the summation, and I was getting at, from n, small n equals 1 to n minus 1. Actually, yeah, this would be n minus 1 points. If we actually call this the 0 point. I labeled these wrong, so I'm going to fix it in a second. So this would be the 0 point all the way up, and this would be n minus 1. That's not important right now. It's going to be times a term a to the small n. Here a is equal to e to the j psi, and that's psi. Now, do you remember I was doing a bunch of derivations to chomp it down to that point? Do y'all remember this class? I got heads shaking. I'm assuming you do. I'm just rewriting what I had on the board. I'm going to do something with the n one is n minus 1, not n, to be consistent with Dr. Wentworth's notation. Right? We start at 0, we end at n minus 1. You're going to see this all comes together. That's what A is in that equation. Are we clear then? It's really what? E to the j sine ultimately, right? All right, now, when you do this, did I show you how that boils down to 1 minus a? I think I did. So this boils down to 1 minus a to the n over 1 minus a. And then, and you don't have to write this, but if you want to, you can. That's a to the n over 2 times a to the minus n over 2 minus a to the n over 2 over a to the, this is n psi. I didn't put the psi in there. It should be a to the psi. I'm so sorry. Well, actually, no, I can leave that off because I've got it right there. I'm gonna fly here. That's just n. Sorry. And then this, just for completeness sake, would be a to the n over 2 let's just say to the 1/2 Now the reason I did that is because a is this term right here. What I end up saying is I have a to the n over 2 minus a to the minus n over 2 with a minus sign coming out. And then then that basically is 2j sine of that angle. Do y'all remember this class? I may remember what I was getting at, right? I'm just trying to get this in terms of the sinc function. So this whole thing, when I replace a by that, and remember what that is, comes down to this. It would be e to the j n psi over 2 over e to the j psi over 2. When you get up to higher level courses and in graduate school, this sort of becomes second nature. And then it's going to be times the sine. Now write this down, n psi over 2, right here. And what I really should do is just break this off and say that's what this is. And I'll write the entirety of the thing. N psi over 2 over the sine of psi over 2. And here's the thing you're going to star. This right here, you can call AF, and if you put a sub E here, or in some way indicate, this is going to be the antenna factor used to multiply the electric field or magnetic field of the element. Are you with me? So this has nothing to do with the type of element, it has to do with only the array. And it's real important that you notice this is not squared. This right here is the array factor. Now, the total electric field for my little array there would be equal to the element pattern times the array factor. Box that. By the same token, the magnetic field would just be the electric field total divided by eta. Are you clear in this class? How many understand what I did and why I did it? Would you like to sit up front because you're scribing this whole thing? And I kind of feel bad for you that far away. All right, now if you need me to do anything to clarify something, just let me know. And I really appreciate you doing it. Are you helping her too? Thank you. Well, I got the two of you. All right, now, one thing I'm going to say is, are you with me so far? This is ultimately the thing you need to know right there for what you multiply the element's electric field by to get the total electric field enhancement. All right? What do you think you do with power? Anyone want that? If that's the electric field, how can we get the power, obviously? Power, remember, you're far from. What would the power density be? Let me ask you that.
That squared over
1/2 magnitude, assuming it's a lossless region and antennas 99% of the time, maybe 100 almost, only work in lossless regions. You don't use an antenna generally in a very low, I mean you can. I say this, I'm very careful. Microwave technically is a lossy thing. Anyway, make a long story short, usually when we talk about antenna engineering and antennas in general, they're in the atmosphere or in space. Low loss. High loss situations, we don't even consider it an antenna. Usually, it's a probe. Anyway, that's the electric field. I'm going to do an example of that, but right next to this, if we wanted to know what the power density increase would be to P average, call it P average total, all we need to do is take the power, average power density, at a given point, or at a given angle phi, or theta, all right? Take that, so that's a power density, and we know it's going to be the AR direction, correct? You can put it on there if you want. We're assuming this array is centered at the origin, and it's just times this array factor squared, magnitude. So if I take that array factor and square it, I get rid of this phase business, and I just have the sine of n psi over 2 over the sine of psi over 2 squared. And you can block that. Wentworth's book does this. He calls this term right here is F array, I believe. You can check in his book. In Dr. Wentworth's book, it's meant to be very practical. I'm looking for it. Yeah, this is on page 471 in the middle. It's in equation 895. He has it boxed, and he has it for pi over 2 is theta, but this is generally true. Whatever you take, the power density, that F unit he has there is really going to be the power density of the individual element at a point. And you just multiply it by the array, and you notice how, where does it have that thing? I'm missing seeing something. There's a point where he has that. Oh, there it is. This is on page 474, equation 8101. Shows you the sine squared of n psi over 2 divided by the sine squared of psi over 2. Do you all see that? It's equation 8101 on page 474. You can box it. I'm showing you what happens, how you get there. This equation is the array factor. This is for power. This is for electric field. Obviously, if you have the electric field, you can take it, square it, divide it by 280, you've got the power. So it's kind of all-inclusive. Now, one of the things that's important to take a look at when you do this is the actual patterns that will develop with different arrays. All right? And here's what we usually do. Usually they worry about power patterns. We don't worry about the elements pattern first. We take a look at this, okay? We just want to see how the sine squared terms are going to vary versus psi. And so in the very beginning, what I like to do is show you something just about what the sine of n psi over 2 divided by sine of psi over 2 looks like. Anybody want to take a guess? Well, what's one weird function that has a sine divided by something that we use in communications all the time? That has to do with the Fourier transform of a pulse function. Anybody?
Sync.
Sync function, right? If you're an engineer, you're going to use sync probably nearly as much as cosine and sine. It's the way it is. You can't get around it. So, what I'm going to do is plot. I want to just talk a little bit about this functional behavior because the signature it has, it's so important. Going to leave it right there. All right, so first of all, let's just talk about a sync function. If we have f of x equal to the sync of x, there's two ways to represent sync, by the way. I'm going to choose the way you saw it in your, I think you saw it in your signals and systems course. And that was equal to the sine of x, right, over x, right? How many remember that? This is standard. Now, when you do this, first thing you always want to do is take a look at a plot of a functional form that you're relating something to. So if I just take a look at the magnitude of f of x over x, here's the way you do it. You always take a look at the top function. See that sine of x? At 0, it is 0, right? And it's divided by x. At 0, x is 0, right? When x is 0, you got 0, but it's undefined, right? So you have to use L'Hopital's rule. Take the derivative of the top, which would be cosine of x, right? The derivative of the bottom, which is 1, and you evaluate that at the point, the singularity, which is at 0. Its value is 1. Now, the next thing you always do, graphing the function, is you look for what's called the first 0, where the function has a value of 0. So here, and I'm just looking at the top point, right? What is it going to be? Well, sine of pi over 2 is the first time after the actual 0 value of x that you get a 0, isn't it? Or, I'm sorry, sine of pi, right? Correct, class? Sine of pi is 0, correct? So you come out here and you put pi down. Now, it goes to relative maximum at 3/2 pi. It goes back to 0 again at 2 pi, right? And we can make the argument at n pi goes to 0. It'll be a symmetric function. So it's going to be the same for positive variance as it is for negative variance. You can fold about the vertical axis, the actual signature and the positive for positive x onto the negative axis. And this is what it's going to look like. Okay? With me? How many remember it now? The sync function, right? You're going to have to know that pretty well. All right. Now, if you take a look at what I'm going to show you, the sine, call it f of psi, and this is going to be the magnitude of the sine of n psi over 2 over the sine of psi over 2. Here's how we deal with that function. For n large, so somebody should think, what is large? 5 or more, 6 or more, something like that. Really, at this point, it doesn't matter. Just a lot of them, more than one, more than 3, say, or 4. All right, when you take a look at this for n large, and you're plotting f of psi, I call it f of psi, just function form. All right, here's how you deal with a function like this. You could say I'm going to evaluate it, and this is versus psi, it's psi equals 0, right? But, and then I have to use L'Hopital's rule. But I'm going to make this argument. You know, when sine is small, right? The sine of x is about x, isn't it? So really I could say that for at least small values is just psi over 2. Agreed, class? We want to look at it about 0. So what happens there? Well, my first 0 happens when n psi over 2 is equal to pi. Or we can say the first 0 occurs when psi itself is 2 pi over n. Can you all see that? All right? Are you with me? Because I'm just looking at the upper term. The lower one, as long as I'm around 0, not at 0, that's a small value. I'm just looking at the 0. Now, what's the value going to be? Well, it's going to be, it's going to be 0 at this point. So this first 0 is the 2 pi over n, right? And the actual functional form, this function, now this is important, at 0, when you do L'Hopital's rule, take the derivative of the top, derivative of the bottom, you're going to get the value, the n psi over 2 comes out in front, you get a cosine argument. It's divided by psi over 2. You actually get a peak value here of n. All right? I'm just trying to show you roughly what this thing looks like. I'm going to put the sign back in. And here's what it does. Now that's versus psi. One thing you can see is it looks a lot like a sinc function. As a matter of fact, around 0, close to psi equals 0, it is a sinc function for all intents and purposes. And the neat thing to see is this. This is the important thing. The larger the number n, the narrower the first null is, or the main beam. Do you all follow me in that class? Now I know this is psi, it's not theta. We'd have to do a transition to theta. But this is when they talk about how to plot antenna patterns, first order, you always do this. You find out what the pattern looks like versus psi. And it's pretty obvious, right? Are you all with me so far? Now, how does this, I'm trying to show you what the function looks like. Well, when I look at this function right here, and knowing that psi itself is equal to beta d cosine of phi plus alpha, I can see that the first time this function goes to 0 right here is when 2 pi over n is equal to psi, right? And I put 2 pi over n here equal to beta d cosine of phi plus alpha, and I can solve for phi where the first 0 is. Do you all follow me? Now, you're probably thinking, how much am I going to be responsible for? And I'll get to that. But fundamentally, do you all see what's going on here? After you sketch a few of these patterns, it becomes real clear to you how this behavior is. So, it all depends on alpha, and it depends on beta, or I should say d, the separation distance. And separation distance will always be in wavelengths. So let me just do something too. Usually when we talk about psi, forget beta, just right off the bat put 2 pi over lambda here, and then put d in terms of wavelengths. Then put cosine of phi plus alpha. And that way, if it's a half wavelength separation between each element, well, lambda over 2 divided by lambda is just 1/2 times 2 pi would just be pi. Do you all follow me? And you can go through and figure out for any value of d what the coefficient of the cosine of phi will be. I'm going to do a simple one, all right? Now, you always worry when you plot these things about the behavior of this guy, because for a lot of these things, at least about the relative maximum, which most people care about, all these zeros, this one, this one, this one, the lower one here is really affecting it. All right, that's just the reality. It's not changing that value much. That's where it goes to zero. So the next logical question is, well, what would these array patterns look like versus different values of n and alpha? And what really happens is when we do what's called beam steering. Have you heard beam steering before? The term? How many have? Beam steering is taking the main beam from an antenna array and relocating it. Now, y'all know those, you've seen these radar dishes that revolve, haven't you? They're effectively beam steering by literally taking the antenna and physically moving it. It's usually a parabolic dish or semi-parabolic. But what an array does, an electronic array, it steers the beam by adjusting the phase on the currents. All right, and that's a critical factor. You're going to see this in some of the problems you get. So what I'm going to do next is I'm going to show you a simple example. And I want to tell you, Dr. Riggs' antenna class goes into the entirety of arrays, not just linear one-dimensional arrays with constant currents, but they'll have variable currents that are selected to achieve things like minimum sideband, or I should say, anytime you have, I shouldn't say sideband, what I should say is there's a main beam for an antenna, and then there are unwanted effects that are called side lobes, where you can actually distribute the current's magnitude to minimize the side lobes, and things that are called Chebyshev, sorry, not Chebyshev, but there's polynomials, Legendre polynomials, and other things where you develop weighting constant for the current on each one of those antenna elements. But you can do the heck out of it. So, next thing I want to show you is a simple example. Now, Dr. Winkler's book shows you a very simple example of this is on page 476. He says a 5-element dipole. This is in the XY plane and it's versus phi. And it's for example 8-9. Not sure what that is. Oh, it's the prior one there. It shows you the actual pattern you get. All right, just write that down. Now, I want to tell you, you look at that thing, you're wondering, how in the world did he figure that out? He didn't. He used MATLAB to predict it. And most of the time when you have many elements, the only thing you're really worried about is using your computer to predict the plot, all right? But that thing can be beam steered, and I'll show you that a little later, either today or on Friday. So, here's a simple problem. Oh, one other thing before I say that. If you have, and you don't need to write this down, just hear me. Anytime you have an array like this, the only measurement of importance angularly is for the array factor is going to be the distance, or I should say the angle between the actual array itself all the way out there, the array itself and the radius vector. Right? That's the only thing of importance. Sorry, it's not a weather announcement this time. Do you guys get those alerts on your phone for severe weather? That one wasn't. So this is the only thing of importance when you have to calculate the array factor. Now, that means one thing. The array factor here would only be a variation versus the angle this way. And if I looked at antennas that I have all my antennas this way, I'm going to just show you 3 antennas this way, separated by a distance d. Call this the z, that the x, and that the y. Well, the actual antenna factor itself, and this is what Whitmore strives for, the angle of interest would be the angle the radius vector makes, really, with respect to this angle. Do y'all see this, class? I'm trying to show it in the XY plane. It wouldn't be the angle theta because the array is along the XY plane. And if we were looking at the field value, the electric field value just in that plane, in the XY plane, only phi would matter. Now, the actual electric field from any antenna in that direction has to do with this angle, right? So if you wanted the total field at a point, say you were in the XY plane, you would take the electric field from this element, but it would be at theta equals 90 degrees. Do y'all see this, class? By the way, it would be a maximum. And then you would multiply it by the antenna factor there. Likewise, if you want, and I don't want to get too, I don't want to confuse you too much about this because you can go a lot of different ways. If you had some radius vector r that had an angle theta here, but its projection here, I guess we could call it rho, was really equal to what? The sine of theta times r would be rho. You follow me? I'm just taking the shadow that would cast on the xy plane. This would be the angle you would worry about between the array and that rho value to get the actual array factors effect on the electric field. Then you would use, if it was a short dipole, the sine of this angle times eta times beta times I naught times L, the length times e to the minus j beta r over 4 pi r to get the value of the electric field caused by the individual elements. And I don't want to belabor that point. I want you to focus on the effects of the array. So, here's a question, and a good one. If I have an antenna like, or better yet, let me just bring it down and make it real simple. Suppose I have, this is the ultimate simple problem, I have two elements separated by a distance d. This is going to have I naught. This has I naught e to the j alpha. All right. And I'm going to, for the sake of argument, make d equal to lambda over 2. That's a half-wave spacing. This is, by the way, an extreme. Because any more than that, and you get something where you can't tell which main beam, where the main beam is directed, and I'll explain that in a bit. In other words, you get a repetitive pattern where because it's longer than a half-wave. Now, if I look at this, this would be the angle phi. With me so far, everyone? And now, what I'm going to do is erase that to go here. You know, by the way, this is the quietest class today for some reason, and I'm not sure why. And the day after something very tragic, like the loss of the national title, silence in the classroom. But is there something going on, or are you just naturally quite tired? Maybe the weather.
Wednesday, maybe.
It's Wednesday. Okay. Hump day. All right, back to this problem, because this is kind of interesting. So if we want, the first thing is, suppose I want just the array's factor itself, right? So start by doing psi. This is how you always start. Psi itself is beta d cosine of phi plus alpha. Now I have to define alpha. We're going to start with alpha equals 0. Fair enough? Make it easy. Therefore, psi itself would be beta, which is 2 pi over lambda, times d. I made d lambda over 2 times the cosine of phi. And therefore, that's just pi cosine of phi. You agree with me? All right. Now, what's the effect on the electric field? I'm going to put a sub e there. This is the array factor. I multiply the electric field of any element by. Well, that is equal to the sine, just magnitude, just take the magnitude, don't worry about the phase. The sine of n psi, n is 2. I didn't state that. Just the number of elements, 2 elements. It's 2, it's n psi over 2, or it's really just sine of psi over the sine of psi over 2. Now just think for a second, because n is 2, right? N psi over 2 is just psi, and then just psi over 2 here. Agreed, class? I used to whiz through this, I don't anymore. I assume people are trying to think through. Now, when I replace the angle by that, I get the magnitude of the sine of psi, or just pi cosine of phi, divided by the sine of, now it's pi over 2 cosine of phi. Y'all agree with that?
No, just be squared.
No, this is for the electric field. Remember, the electric field doesn't have the square. The power will. If we getting power, we take it. I'm so glad you asked that. I would take the, whatever I multiply the E field by and square it, right? Then I take the power density of the isotropic element, or I mean of the element I'm using, and multiply it by that squared.
So
Okay?
this is just the F array.
This is what I'm calling AE for it's the enhancement of the E field only. The power will be this square.
Okay.
All right. Did I make myself clear about that earlier?
Earlier when you used multiply by e to the jn, what's
No, that was the phase though. E to the j n psi over 2 divided by e to the j psi over 2. E to the j anything is an angle. Here I'm just talking about the magnitude. That's the only thing you really care about. You don't care about phase. I mean, if you're in the real world, you're doing measurements. You can care less what the phase of the electric field is at 30 meters from the antenna. Now, if you're doing something with synchronization and stuff with radar, it's a little different, but we're far from that. All right. Is everybody with me so far? So here's an obvious thing. What does this look like versus not psi, but phi? And it's a magnitude. So I always start at 0. So what's the cosine of 0, anyone? This is going to be versus phi. And this is just going to be the magnitude kind of factor. Well, I'm starting at 0. Cosine of 0 is, together now, 1, right? I don't know if you're, okay, it's 1, right? So therefore I'm just multiplying pi by 1. What is the sine of pi? Sine of 180 degrees is 0, right? All right, down here, let's see if we have a singularity. Cosine of 0 is 1, right? Therefore, it'd be the sine of pi over 2 or 90 degrees. Sine of pi over 2 or 90 degrees is? So I got 0 over 1, it's 0. Good. That means there's a null here. I mean, that's a null right here. It starts at 0. I'm just applying it versus phi. Let's keep going up. Where's the first time this is the cosine of phi? In other words, I know that that's going to be 0, right? But what's going to happen here? Well, the cosine of, say, 45 degrees. Let's try that. Cosine of 45 degrees is 1 over square root of 2, right? Then I have pi over the square root of 2 here, right? All right, pi over the square root of 2, I don't know. Somewhere between 45 and 60, something like that, right? If I look at, yeah, 45 and 60. When I think about that, the sine has a value, right? It's about 0.866. Now what about down here? Cosine of 45 is 1 over square root of 2. Sine of pi over 2 divided by square root of 2 is less than 45. It's smaller, right? It's still got big. But when is the next 0? As a matter of fact, if I sketch this, what you'll see is this. Now here the radius vector r, right there that I'm graphing, would be proportional to the value of the array factor. This is the way they use it. So this is called a polar plot. And this would be the angle, right? let me just do it this way. I'm going to graph it in a polar fashion, not linear. This will be the angle of phi. Well, where's the next zero going to occur? We know there's a zero when the angle is zero, which means the actual, I'm going to do a polar plot here. I didn't originally, but I'm going to do it to show you. You all with me? Keep going. Where's the next zero?
Pi.
Where is it?
Pi.
Well, where's this zero? We know it's zero at zero. I mean, at what? At pi or? Yeah, what is the cosine of what angle is zero? Pi over 2. So when the angle is pi over 2, this is a 0, right? And this still has a value if you take a look at that, right? So there's another 0 up here. And what you're actually going to get, he shows this. This is hard to show here. Is that. And he shows this exact pattern. You can plot many points and see that's what it is. And that's shown on page 472, figure B. He shows the antenna elements, their vertical dipoles, but he takes the plot in the XY plane. Now, here's a comment. I want you to think about this. What is this really saying? Well, it's saying that the electric field is a maximum off the end of the array, right? Think about this. There's the array. When that radius vector r has an angle of 0, that's that way. That's where the electric field's a max, right? Isn't it? Or is it? I think I did that wrong. I did. Let me do that again. I should have said it's perpendicular. Here's the thing, because there's no phase difference. And I'm going to do a polar plot. There's the origin. What it'll look like is this. I had 90 degrees. This would be the polar plot. Off the array, this would be the angle phi right here. Along the edge of the array, it's 0 this way. But it's a maximum perpendicular. Now let me try to explain why, and I think you'll catch my drift. Think about this. This is separated by pi over 2. How many degrees is a half wavelength? Full wavelength is 360, right? Half a wavelength would be 180 degrees, right? Now think about a wave starting here and propagating. Continue. It would be 180 degrees out of phase with the wave starting here and propagating, right? 180 degree phase change from an equal current means they'll cancel. The electric fields will cancel if the elements are identical. So you're going to get perfect cancellation that way, perfect cancellation this way. Because alpha was 0, if I look, the phase here is the same here, and therefore if I'm vertically upward, it will be perfect constructive interference. So I get a maximum there. You follow me on this, class? That's the reason. So this is what the beam would look like. And I drew it there. I could probably just superimpose this right here. For this particular configuration, here would be the actual antenna factor plotted in magnitude. That's what it would look like. It's a dumbbell. And he shows this in his plot on that page. Now, what if I wanted to steer that in another direction? Now, just think about this from what I told you when I said here that there's a 180 degree phase change from here to here, right? What if I wanted to steer the beam to have a minimum in this direction? Remember, you're going straight up, right? Then I'd want the phase of this one, or I should say the phase of that one, to be 180 degrees different than the phase of this one. Does that make sense to you? Right? Think about it. If they're going straight up, they're going the same distance r, right? Well, if one has got a phase of 0 and the other has a phase of 180 degrees, then the wave fronts as they add together, the distance will cancel exactly. So the way you would beam steer is by changing alpha, and if alpha was equal to 180 degrees, or pi radians, then this whole pattern would just turn and do this. Now you'll see what I'm talking about when I give you some exercises. And what you can find with a lot of patterns, and this is just an added number, If you talk about a typical antenna pattern, you're gonna have a main beam, and they're unavoidable. You get what are called side lobes. These are generally very in line, but they're unavoidable. This is the main beam. There's all sorts of ways to minimize those values, the value, how big of a bulge. But then we steer this beam electronically. This whole pattern will shift where the main beam can be steered to some angle phi prime by adjusting phase. You're going to see this. You can actually calculate the phase adjustment when you want the main beam at any angle phi. This is getting a little too far off the topic, but we can get into the weeds and really make this thing so you can design it a linear array to do whatever you want. But that's the benefit of an array. Now the gain, or the directivity, because power is proportional to n squared, the directivity goes up by a factor of n squared, the maximum directivity. Do you follow me on this, class? But the electric field or H field will only go up by a factor of n because it's related to the square root of power. And that's really arrays in a nutshell. When I give you a few problems to do, all this stuff will come out. Now I'm going to ask you to do a MATLAB problem for Friday. I know I don't talk that much about MATLAB, or Octave, or Python. Octave is free. Does everybody know that? I use Octave a lot at home for simple stuff. I use MATLAB and I'll download the FlexLM license, but I get tired of having my computer tell me it doesn't have the FlexLM license, because it'll happen. There's some sort of time I have with that before it tells me I'm no longer valid. And I don't use cracks, so I know all about it. Oh, Dr. Baginski, here's one I got. I cracked it. No, don't do it. That doesn't look good on the clearance. Have you used any pirate stuff? Sure, all the time. That's a good way to get checked. Some of you are going to have cleared work. Does anybody here